I'm Jesse Galef. I work with the machine learning team, mostly interpretability for machine learning tools, but I'm going to be wandering around acting as TA today, helping out.
Okay, and down there we have Avery, and he's our technical PM, and he's also going to help. So we are like 3 people for your convenience. And so the way we thought structuring this, I put this notebook in Pathable, but it's also, if you don't have Pathable, you don't want to go to Pathable, you can use that. Can you read the link? It's going to be the same notebook. So the idea is to make this a bit more interactive. So go grab the notebook, because we're going to do this together. This is a workshop, not really a presentation. And the idea behind the workshop is we had a lot of talks about functionality, what's new, what's going to be, what was in the past. The idea here was let's look at the whole pipeline. Yeah? Let's have people hands-on try the full thing. And we went with Jesse on Kaggle. We grab a data set. Actually, you can grab it from the notebook. It's like everything, like it's part of it is to download and extract it, and you start doing analysis on that. So the idea is to basically, to go through together the basic pipeline of machine learning. The names might vary, but ideally you want to acquire your data in some way. You want to clean it up. You want to look at it, do some sort of pre-analysis, visualization, feature engineering, or selection. You want to train your models, and then you want to analyze the result of the training. And at the end, it can be deployment. We're not going to go till that point. We don't have time. But you could deploy it. You could write a report. It really depends on your specific application. Like if it is a continuous integration system, you might want to, create an API endpoint that runs a model. It really depends on the application at that point. Okay, so this data set is from the UCI website. It's called Student Performance. In the next slide, I also put directly the link to that, so you can do this thing entirely in Notebook. But if you want to look at that, you can simply click here, and this will take you to this website. So we can see some stuff here. Don't read too much, because we want to do the analysis ourselves. Just starting from data. Okay, so was it possible to grab the notebook? Do you people have it? Yes. Yes. So. Okay. Let's move slowly. First thing. Okay. Each slide is structured this way. There are like few points, that things we're going to do. And then the solution is like how I would do that. Maybe not the best way, is just one way. Yeah, just so you don't pound me. But like you can open, like these are the same cells. Hopefully it should be the same across every slide. You open them, and there's like code to solve that specific point. So if you are stuck or you want ideas, or you're just bored, you want to go ahead, you can look at that. But let's try to do this together, and then we can check out the solution. Okay, so we have a URL. How do we get this stuff, the documented that URL downloaded on our machine? Anybody? Of course, there's a function for that. How do we? Okay, let's step back. How do we find the function for that? Import is working, but this is a zip archive. I want to uncompress it, so I just want to download the data on my local machine. No. How do I get that data from the internet to how do I save it? Basically, how do I save that file? Yes, that's the one. So one thing I typically do to don't have to deal with the relative path. I set my working directory to my notebook directory, which is something internal WTC blah blah blah. So in this case, like everything I save and compress, but it will naturally go there and not clutter my home folder. And oh, where did it go? Okay. So the function is indeed URL download. We take this. you put it in URL download, and I think it by default it goes to a temporary file. So, oh, come on. Yeah, okay, nice. In the template, the key modifiers are not working. What are you doing? Just still not used to the new thing. Okay, so you do this, and then you have this file. If I click here, this file is in here. It's going to be this one. I already uncompressed it before to test it, but don't look at that. So this is the archive. Step one, I have it on my computer. Of course, this works generally, not just for this specific thing. Step two, I need to see what's in the archive. So how do I do it? Anybody has tried to uncompress? I didn't know even that you could uncompress zip archives in Mathematica. Apparently you can. But okay, let's see. We don't know. Let's say extract archive, or maybe zip. Create. Oh, here it is. Okay. Can you read it? Is it big enough? Maybe I can make the documentation bigger. We're going to use it. Okay. This makes sort of sense. Let's see. Extractatize source directory pattern. Yes. Okay, this is what I want. So I'm going to go here, extract archive of, I guess, %, my previous file. And wait, oh, I did it before. So let me do 2% and do override target true. Okay, here it is. So this archive contains a bunch of things. So this problem is student performance estimation, given a bunch of parameters that have been acquired through questionnaire. And we have 2 files for 2 different classes, mathematics and Portuguese. I'm going to look at mathematics, but yeah, it doesn't really matter. You can of course generalize the content to these to whatever. There's an R script to merge the 2 based on the same features. I'm not going to use that, but you can do a more like compound analysis using both class code for both classes. And there's some student txt file that explains a bit what's in each column. Okay, so step 1, as I said, I'm going to take the math one, and I want to bring it in as a data set to start the analysis. Okay, so somebody said before, we have a function called import. Import does many things, deals with many formats. And so what should I type? Import of. Okay. Yeah, it has a, I think the extraction. I will never learn. So back. This, okay. Oof. Yeah, I should deactivate it for these talks. Okay, let's see what it is. I knew this already. So this is CSV, but it's not comma separated, it's semicolon separated. So I already told the guy that we should really have some option to support semicolons here. But in the time being, I didn't want to shy away to show like roadblocks. First roadblock. This is semicolon separated. What do? We need to make it comma separated. Comma separated. Ideas. This is a list of strings. List of strings. String replace. Yes, that's a good one. So I think that all the string functions are listable. They work on a single string or a list of strings. This is a matrix of strings. So I'm going to use a function to dig inside. In this case, like map. So something like string replace. I think this has a carried form, so I can probably just do this. And at this point, I can just say that don't hijack my keys. I can do this at level 2 only. So first level, like level 0 is a whole expression. First level is a vector, but this is a vector of vectors. So I'm going to go down to level 2 where the strings are. I do this. Okay, this makes sense. So this is sort of what I want. We can probably alternatively, if you want to re-import this, there's probably a even neater way of doing this. I can import this as a string. And then I don't need to map. It's just a single string. Yeah. So this is just the whole file content as a string. And stop doing that. And the reason I want this is because now this is basically this same file just dumped as a string in memory. And maybe somebody know we have a variant of import that deals with the serialized content of the file in memory, which is import string, which is doing the same thing, but working on the string representation of the file. So now I'm going to do import string. And now this is a honest CSV file, string representation, bam. So I don't know if you can see it now, is my nice matrix format here. But I want it as a data set. I mean, I could manually create a data set. And if you want to play a bit with data, I encourage you to try it later. But I'm lazy. So I know that imports, many formats have input elements. And so yes, we go to documentation. And we check what is CVS supports. So supports has input elements. Oh, it has data set. It automatically converts stuff to data set. But there's more. Let's go down. There's the input option. And I see that here there's header lines. And I just happen to see that the first line of this CSV file is actually the name of the columns. So I'm just going to modify this to say dataset. And this becomes this. And then I'm going to add header columns. No, header lines, or header lines, sorry. Header lines 1. By the way, we are working with the import-export team to automate a bunch of these things to kind of be a bit more aggressive, if you want, in suggesting these things. But yeah, overall, it's not a big piece of code to do some kind of minimal conformation. Now this is a nice format, and we can start doing some analysis on this. Any questions so far? Does it make sense? I assume so. Okay. This is a bit more difficult, student.txt. So I'm just going to import this and left the exercise to the reader, the same paper. But the solution is there. Is it doable? So you see, this is like this, has a bunch of comments. It has first column. So we should look at the data. We should always look at the data first. Feature is school. They went to one school or the other school. The male, female, the age, if they live in urban or rural area, how big is their family. So we have a bunch of things that we're asking the questionnaire. Mother education, father education, are the parents working together? What's the mother doing? What's the father doing? Why they chose a school? It was close to home. It was a very cool school. They have no idea. Guardian, I try to understand. I don't know if somebody can help me here. Is there in US something like a guardian of a student at school? Is it different from the part? Who are your brothers? Yeah, so I don't understand if you have both parents and they're living together, why it should be one or the other. I have no idea. Anyway, so this is a mysterious feature. Sometimes you do have mysterious features. So I have no idea what is represented exactly. The other are a bit more obvious. We had also more complicated data sets. We picked like kind of a more reasonable one. Travel time, of course, how far you are from a school, study time, number of past failures, if you got support, educational support, family educational support. These extra paid classes around. Jesse was suggesting me that might be a proxy for how rich the family is. We don't know, it could be. And you see there's a bunch of other things that they want to do, that they are doing. If they're in a relationship, might have an impact, we have no idea. Free time. Okay, you see there's a bunch of things. And then there are like actually the scores. So you see this G1, G2, G3, they have like 3 periods and 3 grades. And they all are from 0 to 20. And this school says that if you are below 10, you fail. If you are 10 or above, you pass. So we can basically do two things here. We can try to predict pass or fail, or we can try to predict the actual score. So one is going to be a regression problem. We want to predict a numerical value. One is going to be a classification problem, like just a binary classification in this case. But you can, you can chunk the data in more blocks. There are like several scoring system, A, B, C, D, F. I don't know. It depends on the country. 1, 2, 3, 4, 5 in Germany. So you can chunk that and do a multivariate classification problem to predict those. Okay, so I have one exercise to kind of split that and take out this in 3 columns. It's interesting. It's always nice to be able to work with strings. You can work with regular expressions or with patterns in Mathematica. It's useful to know. So especially if you work with string data, and you almost always work with string data. Okay, then let's do some examples of data cleaning. So in Mathematica, we have, let's check the data sets. I actually didn't save it. I think I saved it on raw data. Yes, here it is. So we have a bunch of yes, no things. But in Mathematica, we have native data types for a bunch of stuff, like quantities, the dates. In this case, Booleans, we have true, false. So you could, in principle, replace all of them, column by column. Now let's just try to do something simple. How do I don't want to have yes, no. I want them to be actually true, false things, so that the system knows that they're Boolean. How do I do that? Okay, give me code. Okay, but that's not called map in the language. Yeah, replace. That's it. Replace. So replace. And what do you have here? We have yes goes to true, and no goes to false. Okay. Let's check. Let's check. Ah, it didn't work. Why? This is subtle. I should have said. Yeah, but why? Replace all will work, but why? And why replace is not working here? No. Is you have to, this you find with the documentation. Always read the documentation. Replace by default works at level 0, so it looks at the whole expression and replace that. And this expression is a data set. It's not yes or no, so it's not going to replace anything. So you can say, for example, replace down to infinity. Infinity. And wait, this should have done it. Okay, replace all is working now. I'm a bit annoyed that. Okay, this is working. Why replace is not? We have some. This is associations. We have some issues, quote unquote, with the how association they tend to grab the arguments. This should have worked. I will look why it doesn't. But replace all, as you said, is working. So this is done one pass. You can. Oh, where was it? Let's put it here. Okay, let's call this data set. And we're here. Okay, so step 1. So you can imagine, in principle, you could have dates. You could just use some quantity object to grab quantities. You can use a date object to convert strings of dates into dates. So you can do data arithmetics. You have other talks around here about these kind of subdomains where you have geo positions, locations, like all these things. The more you convert, the more you bring into the system, the more computation you can do on that in general, as a rule of thumb. Okay, now let's do something a bit more involved. So we could replace again, but we want to basically create a version of this classifier of this data set for our classification problem, where we divide the G3 column between fail and pass. yeah, this binary classification. So this is going to be similar, but how do we do it? What do I use? This is going to be G3. It's a bit weird semantic. We are working on a new data frame-ish format that I hope will work very nicely with machine learning. I have my eye on that. So this will become smoother, but for the time being, dataset can still allow to do that. So any idea how I mean, what I use on the third column to do this? Sorry? Yeah, you can replace again. Yeah, you can replace again, and you can say, for example, if like any number, so that the number is less than 10, this will go to fail. And then I mean, I could say blank pattern or all the rest, but if I want to be sure that there's no crazy other thing, I can be specific, and I say any number where x is greater or equal than 10. This will go to pass. And I was calling that binary. Oh yeah, this has to be in a list. These are those. Ah, no. Okay. Okay, so now if I look at this, this was a fail pass. The first fail pass. Let's check here. 6, 6, 10, 15. Okay, this makes sense. Okay, so now we have data. We could do on cleaning more. This is a nice data set. In general, you have missing data or you have dirty data. This is already quite clean, but you might have like some question marks or dash or ... that you want to. You can use the same idea and replace them with the, like we have this missing symbolic wrapper, which is understood by machine learning functions. They will learn to ignore the feature there. So these are all like little things that are useful. Okay, let's go ahead. We want to do some prior analysis. Of course, it's not going to make sense to do kind of a list plot of a binary variable. I mean, you can, but not very useful. So it's interesting to figure out what are the different types, so we can do different analysis. Ideas. How do I find the type of each column? Well, there are two different points for this reason, but yes. Point one is exactly, you could have, so we have data set, and we could say stay here. We could say, for example, all rows, I remember, no, sorry. This is head, no, you see. This is gonna be, okay, all rows map head. Yes. So this, then you could, for example, count it. So you could say transpose, you make it row base, then you want to count. And you want to check that, sorry, yeah, you want to map counts. Yeah, here it is. So in this case, they're all kind of neat. They're all strings, all integers. In principle, I'm doing counts because it might be that there are, like 99% is one thing and another thing is different. So you can you can start by this one and say, okay, now strings are going to be one type of variable, integer is going to be another type of variable. Head is not super solid, so you might want to use like we have like predicates, like is a numeric queue, then I say that is number. It is a string queue, then I say that it's like kind of a categorical variable. It's date queue. Like if I clean up more things, I have different data types, I can do more. But as you were saying before, we have also like kind of a fast way to do this. You can piggyback on feature extraction, and you can say this. This gives you a feature extractor function. So you see it says type mixed here, nominal, numerical, nominal. So this already knows that, and then we can just do information. You can find this in documentation and feature types. Okay. So already now we have something that you can use for further analysis. Now the keys are the same as the columns, and we have a type. Okay, so let's go to the next one and see things. Okay. I'm using the type in the next one, not in this one. Okay, let's start with some basic thing. We assume there might be some, I assume at least there might be some correlation between the score in the first semester and the last semester, or the second semester and the last semester. We want to plot them to have a look. Yeah, like machine learning engineer, want to know what we're dealing with. So you probably have seen we have several visualization function to do a scatter plot. What are we going to use? Ideas? This plot. That's correct. So I'm going to take my data set, and I'm going to say I want to just G1 and G3. This gives me just these two columns. And then all these functions, they support data set. So I can just do this. And here we are. So we indeed see some correlation. And if you look at G2, see that this is an even stronger correlation, like less variance here in terms of what can be done. Of course, you can, if you look at the documentation for list plot, you can find a bunch of things that might be nice here. For example, you can say axis labels are going to be automatic, and then I'm getting G1, or whatever, G2, G3. So we can start making like more presentation worthy this thing. Or you could say, for example, plot style. And I'm going to combine directives with directive and say point size large and something like opacity, for example. So you can see it a bit better. And I can also make maybe the labels bigger, base style, I don't know, 20. Can you all see now? Okay, so this is just a few things, but now we have the labels. It is bigger. We can read it in the presentation. We have some opacity, so you can immediately see that some like there's more density here than at the side. And of course, it's an art. I'm not claiming to be the master of visualization, but there are different functionalities to do that. Jesse, you are a master of visualization. Okay, you are a vintage master. Thanks for the question. I think those are the point where G3 is 0, yeah, so that the person didn't pass. This point here, they fail with 0. Yeah, there's a bunch of people that fail with 0, and it might be we can check if we check with the first column as well, people who didn't pass the first one. Maybe they drop out. Yeah, like my guess is I would have to call the university and ask, but my guess is that some people didn't pass the first one, and if they didn't show up for the second and third one, they would get 0 so maybe they did up to the you have a non-zero value on the second one, and you have also a bunch of points which is a bit darker here in the origin. So I assume that the origin is that people that didn't pass the second one, also they didn't show up to the second one and the third one, and these people tried the second one, they didn't pass, and they didn't go to the third one. But this is why it's useful to visualize things, because you start asking this kind of question, and you start challenging challenging the data, and more often than not, you find that data are not very clean and not very nice, and you need to write down a bit more of what's going on typically in this kind of wild data set. Okay, so I don't how much time do we have? 27 minutes. Okay, there are some things you can do. For example, this one I'm going to take from the solution because I just want to save a bit of time. You know, we can use a method we used before. It's not entirely new, so I'm just doing this again. So I'm just doing on the data set. I'm just taking column G1, G2, G3, making them all binary pass fail. So I get this thing, and now I can compute all the possible triplets, for example, which is very easy. I've used a function before. Anyone have any idea what the function f should be here? I used it in the previous slide. Yeah, counts. Count needs, I think it needs a pattern. Counts returns the association with key is what it was counted, and then the value is how many of them you have. So in this case, for example, you see I have several triplets. Like fail is it's a substantial one. You have like 100 people there. But also pass. Fortunately, like pass is also sizable, and this is a bit convoluted for like I don't know. I cannot keep more than 3, 4, maybe 5 numbers in my head at the same time. So an exercise I had here is how can we do it only when you know, for couples G2, G3, but only for people that pass G1. So I'm going to take columns. So it's going to be G2, G3, and I want some filter here. Yeah. I could say select G1 is equal to pass. Here it is. Okay, so this is to me is more comprehensible. So we see some people tried the last semester. Sorry, even if they failed the previous one, but in general you see pretty strong correlation. If they pass the second one, they are going to pass the third one. If they fail the second one, they're most likely going to fail the third one. So we already know, and if you read the paper, they suggest you like another challenge, like if you keep G2, is much easier to predict G3. If you want to stress yourself, drop also G2, or maybe drop also G1, and try to see if you can use this kind of socio-economical data to as a proxy for the. My guess is that you cannot, and that this whole thing is overrated. But people are trying very hard. But you see, you can measure how much the accuracy drops if you actually don't count the actual scores. Okay. Now, why did I ask you to take the data types? Because ideally we want to have different visualization for different type of data. Yeah. So I put here like a bunch, like data set with only the column corresponding to numerical features, and then a histogram of each column. So how are we going to do that? What do I put here? It's a bit more convoluted. So ideally, I want all the rows, and here I want a list of columns. And these columns have to be the columns that have numerical in my types here. So how do I find all the keys that correspond to numerical here? Okay. Select. What do I put here? Select takes predicates. So it has to be something that returns true or false. So I want that, yes, hash. This is going to be nominal, numerical, huh? And this has to be what? Equal to numerical. This is a pure function. Okay, now I have my, I brought it down, but now this is an association. I only want the, or a dictionary or whatever. I only want the keys, not the values, because values I know what they are. So how do I get the keys? Keys with the function keys. There's a no, sorry. Okay. So do we have a load of operator forms? So if you don't like pure function and you want something like readable stuff, you can also do this. It's going to be completely the same. So this is an operator is a carried form, yeah. Like if I apply this to something, you know, is this equal to numerical? False. Is numerical equal to numerical? True. But it basically turns like a binary operator in a unary operator. And the advantage is that you can drop it in these places. And even select has a carried form. So I can, if I want to go crazy, I can start doing this. Don't do this at home. And I can probably also do the just at, yeah. So I just show function application everywhere. Position works on association. I don't even know position index. Okay, let me check. Unique element in the list and position to the show. Ah, oh yes, you showed this to me once, and I never used it, so I forgot. Amazing. This is even better. You see, you always find out things. So we want position index, and we want numerical. Bam. Even better. So now this is my list of columns. Put it here. Here it is. Now what I want is what they say. I want a histogram of each column. So I think this is going to be easy. I just do this. Okay, yeah. Or I could do probably normal if I want to keep the. Oh no, sorry. Bad. I understand why he's taking a lot, because he's doing the histogram by rows. So I want to make rows columns and do this. Yeah, here it is. So we see age distribution. These things are, some of them are really kind of ordinal features. And I'm happy to say that this team is working on ordinal scales. So I don't know if Brad already talked about that. He will talk about it. I don't want to spoil anything. But we are ready to jump on that for feature types as soon as we have something like that ready, because you know you have several data sets where you do have numbers that they represent like something bad, medium, good, and you probably want to see it that way. So you can look at the scores at the end, for example. So you see this is what I was talking about, yeah. So you have this is, I don't know, do people normalize test results in the US? This looks like too normal to be true, but this, okay, the G1 is. In Portugal, they do?
No, aren't these students in Portugal?
Oh, they are, maybe. I thought it was Portuguese as a foreign language. See, I didn't read, bad me. And, but you see, this one are like probably people that you were asking before. Yeah, maybe they're dropouts. And there's a bunch here as well. There's more. But the actual people that take the test, I think, they're all pretty normally distributed. Okay, so we have this. Now we can do very easily, we can do the same thing now that you know how to do it. What they have here, we can create a pie chart. Oh no, this nominal was my mistake. This was supposed to be Boolean. So if I do Boolean, and then I do transpose same as before, and then I do pie chart. What did I do? Oh, B, like this? Yeah. Native speakers always have an edge. Okay, what did I do here? I did something wrong. Oh yes, because the histogram is counting. This is not counting. So it's not just pie chart, it's pie chart of the counts, which is a function that we use a lot. And I'm still unhappy. Why I'm still unhappy? I'm mapping counts. This should work. Okay. Why pie chart is not working on this? Let me try to normalize it. Maybe if I do this, it's gonna be happier. Okay, yeah, pretty happy. So now we can see, this is another thing, you can do a multi-column, you can do a grid of these. I'm just not gonna spend too much time here. But school support, not many people. Family support, a bit more. People that get paid, what was the paid? The paid lunch? I know, they paid for extra classes, you're right, okay. So yeah, a lot of people paid for extra classes. And yeah, so one thing is like, this false is yellow, this false is blue. This is like, I'm not a good visualizer, but I know this is bad. So one thing you can probably want to do here is if you do key sort, and you just, this is a composition. I use it when you have, again, unary function, you can easily compose them. So this is a map, and these two things are, like F composed G, they are composed and mapped together. So for each element is doing first the count and then sorting the keys. Okay, now false is coming first because F and T. So first is always yellow, true is always blue. And yeah, you can do the same, and bar chart of a nominal features is going to be the same. I can just take this and put it here and say bar chart here. And the nice thing is that the more functions they have the same syntax, the easier it is to play with them. I really like the visualization suite because they all quack the same. So you can just replace pie chart with bar chart, exactly the same formula. This has a bit more. No, sorry, I want this. I want nominal, not just that, nominal. Okay. So now I have a bit more, like some of them mother job, father job. And then I can clean up the what are the labels under these. So like you can imagine, like if you want to produce a report, like this is quite easy in the end. Like you can go to the ref page, look at the options, and typically drilling down with option, you can do almost whatever you like in terms of presentation of these things. Okay. Let's do some more machine learning thingy because we are running out of time here. Dimensionality reduction. Who's familiar with the dimensionality reduction? What is it? Okay, so he said like you try to, let me paraphrase, embed the feature vector in lower dimensional space, and the idea is to see like this is quite effective. Like imagine you are doing a classification problem. So here I'm using the here. Okay, drop the G3 column and compress each row to 2 dimensions using UMAP method. So I'm gonna talk by doing. So I do dimension reduce, key drop dataset G3. And I'm dropping this because I don't want to consider this. I don't want the method to see that. Because I mean, if you want to predict that, you don't really want to give that information to something that you want to predict. You get better results. Yeah, you get better result here. I want them like 2D, and I want to say method UMAP, which is nice for compressing these features. So if I do this gives me, you see, list of pairs. So there's some feature structure under the hood. Of course, not everything is numerical, but let's say if I call this features UMAP, I was calling it. Okay. So now I can do, yeah, this is big, but I can do a list plot of features UMAP. Okay, so this was group, like I didn't do the plot, but my gut feeling, you can do this as an exercise and tell me that one group is the one that don't pass, and the other group is the one that pass, because there's some, but I might be wrong. You never know. This is a very high dimensional space. And UMAP is a pretty heavy-handed algorithm that tries really to compress hard things that it thinks should go together and separate things that should go apart. So we see two things, but it would be interesting to color this thing a bit based on what you want to predict. So what we can do is we can say, we can grab target. The target I assign it is the third column of my binarized my binarized G3, so with fail and pass. And I have to go a bit faster here because the time is always bad. So I can use this, group by to say everything where target is fail, everything where target is pass, and then I can just where it is. Here, I reopen the same one. Okay. So you see, this is a plot. So now I color these points, these 2D points, based on the value of the third column. But the dimensional deduction didn't see the third column. So this is kind of a preliminary, it's unsupervised. It's kind of a preliminary thing. If you see two blobs of different colors, that's a very good sign. It means that even an unsupervised technique, just by looking at the data, could see two clusters, and so there's very high. I mean, you can already use this as a classifier if it is good enough. From what you see here, there's one area of the 2D space where the people that pass are together. So there's no people that don't pass here, but the rest is a bit mixed. So it's not super trivial. We are going to get good, quite good accuracy in the end, but it's not super trivial. And of course, we have different methods. So there are different ways to do that. So okay, feature structure is done automatically, but is worth to experiment manually to see how it works. We have a feature extraction function, but have you seen that the dimensionality reduction, of course, is calling that internally, because there's no way that you go from a string to a number. So at the end, so it has to build a pipeline where everything becomes a vector, and then the vector is compressed. Let's do some more real training. I don't know if people are keeping up. I hope somebody's keeping up, but you will have more time. You have a notebook, and you can always write me or just an email, and I guess we will help later. Yeah, we can. We'll be around, exactly. So I have 8 minutes, so I have to be a bit faster here. So this you've seen every time, I assume. Yeah, you want randomize the data, train, test, split. In this case, I'm doing a take drop of random sample of data set, and 1/4 I'm taking for testing and dropping from the train part. Then I'm creating a linear regression prediction model. This is a regressor. This is a nice syntax. You can put the data set in and say, I want to predict this column. So I put the whole train in and say, predict column G3. I give a method. I pass a feature extractor that I trained in the previous slide, and I get the predictor function here. It's numeric. I have two things. The data set is numeric, and data set binary is the other one. And then I can start doing some measurement. For example, I can take the mean square error, and people typically check the root mean square error. So I do square root in front, and I measure this on the test set. This is what I can do. This is my first quite easy, already loaded, use predict, select a method, and do it. Of course, you can do the similar thing for classification. I put also a classification problem because these are the two main that you're gonna face in your typical analysis. So now what I do here, same thing, test train, but with dataset binary. And now I do classify on G3, and you see that these classes are fail and pass down here. And now I can measure the accuracy here. And oh yeah, this is because there's a bug in quantities that has not been fixed yet in the build that you have. This is gonna fix the display. But this is 85% accuracy, which is not bad. I think if you drop G2, it goes down to something like 60 or 70 something. So it really drops. And then there's something that you probably always want to do, at least as a comparison. Let the machine learning automation. We were going to have a talk on Friday about what the automation is doing exactly, but give it a try with the automation. So we've worked hard on that. You see, I say same syntax, train binary G3. I pass the validation set because I want my automation to do basically automatically what I did before, measure the accuracy. And I just give it a bit more time. So I say, I want quality performance. I don't care much if it is low to train, and use at least 10 seconds because this is a small problem. It's going to be fast, but I want it to push a bit. And see, it starts training. This is a very small data set, so it starts from small amount of examples and goes up, trying to refine, and tries different methods. And then you can compare the accuracy of the two classifiers. So I go from 85 to 92, and this 92 simply because it did hyperparameter exploration, not just of the method, but between methods. And if you see the one that wins here is not linear regression, is a gradient boosted tree. So this is an ensemble tree model that apparently is performing better. You could have done that manually. You can set up a table and do the training, but this thing is helping a lot. Is doing cross validation inside on the smaller groups, and yeah, I mean, try that and come on Friday if you want to know more about how this works internally. Some metrics, of course, all these things are objects for a reason. You can extract informations. This will tell you, a bunch of things, how fast it is, the accuracy. But then you can query you can put some second argument here and ask for more specific things. For example, here I put this thing here. We revamped the plots a bit for this version. So the basic plot gives you learning curve, number of example grows, and this is the cross entropy goes down, and accuracy goes up, hopefully. And this is what we tried. So each line here is a different method with different hyperparameters that was optimized under the hood. So we tried different families, tree-based model, linear model, non-linear model, the nearest neighbors. So there's a bunch of things. And you can check like up F1 score. You can get the confusion metrics. And another thing that you can get since a few versions is, and I really need to wrap up, to try to guess properties of these models. So why the model is giving the answer that it's giving. And with this many features, this takes a bit, but you can try to compute the impact. Jesse, if you have a question for this, Jesse is our man. So basically, for each feature, you can try to remove it, add it, remove all the others in combination, see how it will affect the final performance, and say, okay, G2, you see, it has both a very big positive impact and a very big negative impact. It's all across the board. So there's a huge impact, both positive and negative, of a feature G2, which is what we expected. But for example, then the third one is absences, like people skipping classes. So people skipping classes actually also have an effect on G3, and so on and so forth. Like you can see like a very narrow distribution means around 0 means there's almost no effect. It doesn't matter if it was big or small, there's almost no effect. And then you, yeah, I was also thinking about that. I mean, I was skipping classes to study my time. So I don't know if in Portugal you can do that, but that would correlate positively with the final score. And here you can see that you can dig down and try to find the correlation between the impact and the feature value. So for example, you can see G1 is a positive correlation, a bit weaker. G2 is a very strong positive correlation. Age is going down a little bit, not much. I assume, all the students taking the same level exam, they probably failed before, or like in this, but not so strong. Sex, of course, as you expect. We tried also other data sets. There's always a confirmation that in math, male kids are a bit better. In humanities, female kids are a bit better. And you see this absences correlation here that Jesse was saying. And then you can also look at individual examples and see, this is very nice, how each feature is impacting the final result. So I'm doing this on the predictor. So the final result is the actual score here. And you can see, for example, this student, there's the impact of G2 that brought it down a bit. Failures, for example, this is probably a student that's failed in previous years. And this brings a lot down. And then there are like each feature corrects that. So they are like sorted by average correction here. So if you go down on average from a full data set is less and less important. So like every time is, for example, activities, maybe this person does a lot of sport. You have to dig down. Okay, I'm at the end here. But this is very useful to dig down and analyze individual examples and see hopefully why your model took that decision. Okay, so I hope this was useful. I put a lot of references here in terms of guides, blogs. There's a book by our former lead developer, Etienne, a lot of community posts. Please go there, read, ask me questions if you find something that you don't understand. I hope this was useful. Thank you.